All right, thank you everyone for coming, and thanks Willow for the introduction and the previous talk on BinSparse. Today I'm going to talk about another standardization effort called the Sparse BLAS. And unfortunately, there's not going to be a lot of Julia in this talk. There is going to be a lot of C++. But Willow and I hope that maybe there can be some, coordination between the Sparse BLAS community, the Julia community, about what are the right interfaces, and we can see how we can work together to move this forward. But please do feel free to stop me. I have a couple of points in the talk where I'll try to stop and ask questions, but also feel free to interrupt me. So I don't think this needs much motivation for this audience, but I'll just have a couple of slides to talk about why sparse matrices are important. And I think the first reason that sparse matrices are important is if we have sparse data and we want to perform sparse computation over that data, right? This includes things like graph computation, iterative methods, all kinds of traditional applications. But also, of increasing importance is dense models where we want to interact with the world. For example, if we want to have a dense recommendation system, the world is sparse. And so we need to have a way to interact with these sparse features and to convert them into some low-dimensional dense features that we can then interact with, right? So this is embeddings are these things that transform our data from a sparse space to a dense space, and they're a part of all kinds of models, in particular recommendation systems, right, which drive a lot of viral trends like Labubu, for example. And so it's important to develop interfaces and support for these kinds of tools. So in this talk, I'll have three parts. I'll talk a little bit about the motivation and the design principles behind the Sparse BLAS, why this is important, and what has come before, where this comes from, what has come before. I'll talk a little bit about the interface itself as it exists, and this is a work in progress. So it's continuously evolving. And then I'll talk a little bit about the reference implementation, which we have this interesting design where from day one, we want to start with multiple vendor backends so that we can run on top of existing frameworks. But we also have a test suite so that we can look at functionality, and then a reference implementation that I've been developing along with some of our other collaborators. So the Sparse BLAS in this current effort is essentially two things. It is an implementation effort to implement our vision for a sparse interface. And currently this is being implemented in C++, although we'll likely have C bindings as well. And it's also a position paper and a specification that we're working on for how to perform a sparse computation. And I'll comment a little bit more towards the end. This is also a community. We've been having a lot of workshops in Knoxville. If you're interested in getting involved, I'll have links to the Google group so that you can be on the mailing list and get involved. But of course, as you've heard about earlier in this session, this is not the first time that people have standardized tools for dealing with sparse matrices and sparse algorithms. One of the most important pieces of related work that I have worked on before in my career is graph BLAS, which luckily we covered at one of the earlier talks. But graph BLAS provides this API for operating on graphs using the language of linear algebra, and so that corresponds to matrix multiplications and other operations that use arbitrary semirings to execute traditional graph algorithms using all of the tools that we've built over the years for operating on sparse matrices. Now, graph BLAS has made a number of design decisions that allow aggressive optimization, one of which is to have an opaque barrier between what the user has and the user's data and the underlying implementation of the data structure of the graph BLAS matrix and how the operation will be performed, right? So the user essentially provides a series of tuples, and then those tuples are going to be copied into some format that the user does not know, right? And this allows the implementation, and specifically in cuSPARSE Graph BLAS, the most robust Graph BLAS implementation, which is maintained by Tim Davis, there are multiple sparse matrix implementations, even dense matrix implementations that will be used depending on the particular state of the data. And the Graph BLAS API allows this to dynamically switch between these different types of containers based on how the data changes over the course of an algorithm. One of the other things about Graph BLAS is that it has a large set of very expressive operations, including masking over matrix multiplications, which is very important for graph algorithms when you want to avoid things like loops when you're doing a graph traversal, but also things like extract and select. Now, these two things are strengths when it comes to graph algorithms, right? They allow a large collection of implementations, but at least in the case of Sparse BLAS, we felt like these were two weaknesses that we wanted to avoid for the sparse linear algebra case. Number one, because there is an import cost to moving your data into an opaque data structure. Although there are some ways you can get around that, and Tim Davis has worked on that some in cuSPARSE, still we decided to go in a different direction. The second difference is that we wanted to start with basically vendor support based on the existing libraries from day one. So we wanted to avoid introducing operations like masked matrix multiply that don't already have robust support from libraries. One of the other pieces of related work, of course, is a previous Sparse BLAS effort that started in the early 2000s that was quite significant, had a significant spec, had some implementations, but failed to get much vendor support. And in our position paper, we kind of outlined two reasons why we felt this might have been the case. One was that it also had an opaque design, where data had to be copied in and out, right? And this means if you want to use a little bit of the API, right, just to perform one operation that you don't have, there is copying cost to moving data in and out, which for sparse operations can be as expensive as doing the operation itself. So that presents a problem. The second case is the area of focus. The original Sparse BLAS focused mostly on one sparse operations, right, where one of the operations is sparse and the other two are dense, as well as some vector operations. And those operations, while they can be difficult to implement on certain platforms, at least for the machines of the day, were not the most difficult algorithms people wanted to implement, like sparse times sparse. On GPUs, things get a bit more challenging. But this kind of examination of prior work led us to a few design principles. And the first design principle is that we want it to be easy to use a little bit of Sparse BLAS, meaning that the user can have some data, present it to the library to perform one algorithm, and then get the result of that data, understand what the formats are so that they still control that in their application, and get on with their applications. That Sparse BLAS could be one piece of a larger workflow. And as a result of that, as we'll talk about, we decided to use views instead of having opaque objects, where the user understands the data structure of the view and is able to control the output of the format of the data. The second, as I previously discussed, is we want to closely match existing vendor libraries. And to that end, we've, from the start, worked to implement Sparse BLAS on top of multiple vendor backends. And we've been lucky to have people involved from various hardware vendors, from AMD, Intel, obviously, NVIDIA, ARM, and others, so that we can understand the libraries as they currently exist and how we can offer a interface that works for all of the vendors. The second one is to support GPUs, or the third one is to support GPUs, right, which is an important application use case today, and to offer as unified an interface as we can for using GPUs across all the different vendors. And finally, of course, solving what we consider to be the whole problem, right, of SPMM and sparse times dense, but also sparse times sparse problems. And we're also focusing on a few other problems like SDMM that are kind of emerging in machine learning workloads. Okay, I want to pause just for a second before I move on to talking about the interface, if there are any quick questions. All right, I will continue. So I will, for purposes of time, I'll move through this fairly quickly. But just from a C++ perspective, I want to draw a distinction between an object or a container that owns its data and a view. So an object is something that owns data inside of it. When you create one, it will allocate data. And when you move data into a container, generally there is a copying cost associated with that. And when you create a new copy of an object or a container, it's going to copy all of that data over into a new object, right? A view, by comparison, is a lightweight object that refers to data that is owned by someone else. And so as a result, there are limitations on what can be done with view, right? The view by itself cannot dynamically resize itself. But also, a view is trivial to create. There is a constant overhead associated with just creating this wrapper that describes how data is already living in memory, right? And so we decided to use views in Sparse BLAS as a way to allow users to plug in their data into the library. So as you can see on the slide, right, we have a CSR view where the user can specify the scalar type of the values of their data, also optionally the index and offset types that are used to refer to data. And they can pass in either pointers to their data or views of their data in a couple of different ways to produce this matrix view and then pass it into Sparse BLAS algorithms. And also you can see we're trying to integrate with existing C++ tools like spans and MD spans that already reference dense data. Now when it comes to two sparse operations where the output is sparse, we still try to maintain this transparency. The rationale being that we want the user to be able to control what the output of the data is, because at the end of the day, they need to get the matrix back, understand its format, and then be able to reason about and manipulate that data in the rest of their application. And so the way that algorithms with a sparse output work is that the user essentially has a two-phase operation where first they compute at least the number of, or the size of the output. The user then allocates enough room for that output, and then there is a fill operation that will ensure that the output is in place and accessible. One other thing about views that I want to mention is that we use them to simplify some other operations, like transposing symbolically a matrix and scaling a matrix. So when you create a transposed view, you don't actually physically transpose the matrix, but instead refer to a symbolic transposition of the matrix, which could be a transposed view object, or it could be essentially converting from a CSR into a CSC. So that you have those different transposed views of the same data. Similarly with scaling, we can simply symbolically scale the data and then fuse the data. This is similar to what's already done, except instead of having multiple descriptors that are passed into the algorithm, we attach these to the object. One other thing is that, and one potential issue with views, one compromise, is that we lose opacity. And so the implementation with just a view is restricted in terms of transformations it can make to the data, right? If we have code like this on the slide, where we create a CSR view and then operate on it repeatedly, there's no opportunity to perform format modifying optimizations. So what we've done in the Sparse BLAS specification is introduce matrix optimization handles that can live on top of views that are objects themselves and can contain optimization data about the matrices that will need to be reallocated dynamically depending on the particular use case. When it comes to GPUs, we depend on execution policies. So various vendors have C++ libraries for dealing with GPUs. And so each of them can define their own execution policies. These can be implementation defined. In practice, what we end up using is thrust as a common C++ layer, where thrust provides essentially a framework for allocating data that lives on a GPU, and then utilities for moving data back and forth and for launching work on GPUs. Okay. All right, so I want to talk about another C++ detail, which is the complexity that can arise when you have all of these different kinds of inputs. So having different kinds of views that you can pass into algorithms is very useful from a user perspective, but when it comes to implementation, if you use traditional methods of defining a function, like on the screen, right, where you explicitly say, this function takes in a CSR view, this function takes in a scaled view, it leads to a combinatorial blowup, right? Because we need to provide individual implementations for all these combinations of views. And so while we don't explicitly specify that this has to be the case in the specification, the way that we implement this in practice is through something called concepts, where a concept typically defines an interface, more formally a binary predicate on a type that we can evaluate at compile time. And using a concept as part of a function interface says that the parameter or the argument that's passed in must match the concept that is defined for the parameter. So for example, we could have a summable concept which says that this is a type that we have the ability to call plus on, and we could specify that using a collection of Boolean statements about that type, that this particular expression is valid. And then if we try to compile this function and we get an incorrect result, basically that particular implementation of our function will not, in C++ language, will not participate in overload resolution. Basically what that means is we'll get a compiler error that says, hey, the thing you put into this was not summable. And if we have multiple implementations that are available with different kinds of concepts for different parameters, it will automatically pick the right one. And so in Sparse BLAS, we have matrix and vector concepts, where essentially we have certain types that are specified to be matrices and certain types that are specified to be vectors. And then we can use those concepts inside of our function definitions, which ends up being very clean. One other thing that we use in the reference implementation that's very useful is something called a requires clause, which can allow additional additional constraints on the function. So for example, we could have a particular implementation of multiply that specifies that A has to be either a CSR matrix or a view on top of a CSR matrix. B has to be dense, and C has to be dense. And then we can use that set of constraints combined with some inspectors that we can use to retrieve information about the stack of views for each matrix to get information about what was passed in. And this is a only slightly simplified version of what SPMM looks like for the MKL backend. So essentially, we take in an an A matrix, which is sparse. We take in a B matrix, which is dense, and output C matrix, which is also dense. And then we can retrieve, is either of these inputs scaled, and also is anything transposed, and use that to call into the pre-existing libraries. Okay, do we have any questions before I go into the reference implementation? Yeah.
So this is mostly, I think, about the interface, but a lot of this seems very C++ heavy. Is there any thought so far on what a C interface looks like? Like, has the working group looked at that at all yet?
Yeah, so we've talked about a C interface. It would probably basically reflect what's in the C++ interface, but with type erasure, where you have like type erased objects, and you have to do a lot of this logic that we do at compile time in C++ at runtime in C. But I think pretty much all the things we do in C++, you could do in C at runtime, but yeah.
Have you thought about multiple dispatch?
Oh. So by multiple dispatch, you mean like runtime multiple dispatch?
Like compile time multiple dispatch like Julia has?
I'm actually not super familiar. Maybe we should talk about this offline. I'm not super familiar with the way that I have read some papers on this a while back, but I'm not on the top of my head exactly how Julia's multiple dispatch works. So yeah, we should talk about it.
But I think perhaps like another way of framing the question is, how do you envision sparse BLAS interacting with a language that is designed to have a rich hierarchy of types, that is designed to, handle some of these kinds of like view objects and symmetry objects with like, language level dispatching?
Yeah, that's a good question. I'm not sure I have a great answer for you off the top of my head, but I think there are definitely opportunities to interact there. But yeah, we should talk about that more offline.
Because
Yeah.
in general, and as I understand it, you basically build expression tree, which then lazily evaluated at the moment when the computation should happen. And there are already several libraries which does that. They don't do it for sparsity in general, in the more generic way, like how you present, but they do it for dense matrices. So have you thought about just extending the existing libraries instead of bringing something new?
Yeah, that's a good question. I think, we haven't thought, I guess eigen would be the main piece of work in C++ there.
I would guess Blaze, but it's my personal preference. Eigen could be as well. They do similar things.
Yeah, that's a good point. We should talk about that offline. Yeah. Okay, so I'll talk very briefly about the reference implementation. So the reference implementation is built on top of ranges, which are a C++ concept for dealing with sequences of values. So essentially, a range is anything that has a begin and end, and then we can iterate through in some way. And there's a hierarchy of ranges in terms of what they allow us to do. For example, a random access range is a range where we can access any element at random and constant time. And a contiguous range is a range that represents a contiguous block of memory. Inside the range library, there's a collection of tools called range adapters that allow us to build views. For example, a transform view takes in a range and then provides a view on top of it that lazily applies some binary function to that range. For example, we could lazily apply every element in a range by 2. So with all these range adapters, they essentially provide a bunch of tools for creating views on top of existing data. And so we can use these to create range adapters that provide structured ways of iterating over sparse matrices using ranges. So for example, for a CSR matrix, right, we can first basically look at the beginning and end of a particular row inside the column indices arrays and the values arrays based on the row pointers. Then we can construct a subrange that consists of the column indices and the values, and then we can zip those two things together. And this provides a way to iterate over any one of our rows in a functional way. What's convenient about this is that it allows us to create a collection of different customization points or range adapters that work for multiple different data structures. For example, iterating over the rows is something that you could do for a CSR matrix, a DCSR matrix, a dense matrix, and potentially for other matrices if you're willing to have non-constant overhead to build that index of how to iterate over rows. And then we can have a collection of concepts that define for a particular data structure what ways of iterating over that data structure we have. And so inside of the backend, essentially, we use these iteration concepts to constrain implementations, which then operate over the data structures and implement SPMM, SPJAM, all of these different operations. And as new views are added, including views like scaled view or transposed view that preserve the iteration methods of the underlying views they were created on top of, we can take advantage of those types inside of the existing algorithms. And this makes it pretty straightforward to have a reference implementation that has very high coverage by using these higher level tools that abstract the lower level ways of iterating over data. Okay, so in conclusion, please come join us or provide us with your input. I have a couple of QR codes for our Google group and our GitHub repo. We have a couple of high-level principles we've tried to use, and we're interested in interacting with the general sparse community and finding ways that we can interact with Julia and other communities. So thank you very much, and I can take any questions.
So what I missed is the actual computations. So is it like heavily header-based library, and all computations are generated from these templates, etc., or is it actually have BLAS, like dense BLAS? It have a C core, or it's have some core which is precompiled, and then you just call it.
Yeah. So the reference implementation is currently just header only. So it has full coverage. Whatever template types you pass in for the values and indices, for example, they will compile as long as they fulfill the predicates. For the vendor implementations, they are limited to the precompiled core that the vendor supports.
What do you mean by vendor implementations?
So in addition to the reference implementation, we also have vendor implementations. Let's see. Yeah, similar to the one that I showed here, for a number of different hardware vendors. They run on top of 1MKL, cuSPARSE, other vendor libraries.
But what is the full list?
The full list of vendors?
Yeah.
It's on the repository. I believe it's, let's see, 1MKL, ARMPL, RockSparse, and cuSPARSE, and AOCL Sparse. That's what we currently support.
All right, so we're pretty much out of time. We have to get to a keynote that's right across the hall that starts in about 5 minutes. So I'm sure there will be plenty of questions for Ben afterwards. But yeah, please go ahead and head to the keynote room if you don't mind.